Hello everyone, my name is Ajay Patidar and I am here with the topic of conformations of butane. So, what we are going to study is different conformations of butane, including staggered conformations, eclipsed conformations, which will be through represented through two different types of method known as Newman projection as well as Sawhorse projection. So, firstly, we will begin with the very definition of conformation. So, what is conformation? So, the different arrangements of atom that can be converted into one another by rotation about a single bond are known as conformations. So, conformations are basically when we pick up the two carbon carbon single bond, when we pick up the carbon carbon single bond and rotate the whole molecule about that bond, then there will be different orientation of that molecule. And when we will rotate the molecule in varied degrees, so different type of orientation will be formed, and those orientations are known as conformations. For example, let us take the first case of when we will rotate the molecule by the degree of by 60-degree angle, then that is the whole different arrangement. Nextly, when we will rotate the molecule by 180-degree, let's say, then that will also be a different arrangement. So these different forms are known as conformations. There are two types of conformations. First one is eclipsed conformation and second one being staggered conformation. So what eclipsed conformation means is that a conformation in which two substituents x and y on adjacent atoms A and B are in closest proximity. What the definition is trying to say is that when the arrangement of the atoms is such that the one one atom or one atom hides the another one. For example, let's say CH3 is in front, which is covered by another CH3 in the back. So that type of conformation in which the adjacent atoms gets covered and the molecule is in closest proximity, that type of conformation is what is known as eclipsed conformation. Nextly, what the staggered conformation means is that when the arrangement of atoms or group of atoms in a molecule results in a 60 degrees of dihedral angle, then the conformation is known as staggered conformation. What the staggered conformation is that, yeah, so this is firstly what we are seeing is that Sawhorse projection of butane molecule. The first one, so the CH3 molecule is in front and one H molecule shown by one H atom shown by dashed lines is going inside the plane, whereas the one H shown by dark line is coming out of the plane. Similarly, that is the case with the back carbon as well. Nextly, the two conformations in Newman projections, the first one being anti and the second one being gauge conformation. So what is happening in the first conformation is that two large groups are in opposite side, and the large groups here are CH3 and CH3. So once when we will view this structure from the side position, then what will happen is that one CH3 is in front, one CH3 is going out of the plane, whereas the one is going downwards in the plane. So they are CH3 molecules are aligned 180 degrees from each other. So that is the highest distance that can be. So what happen is that the repulsion in this case is minimum. That's why uh, the structure will be most stable. That's why we'll study later on that anti-conformation is the most stable of them all. Next one is gauge conformation, which is 60 when in this case the CH3 atoms, the both the CH3 atoms are 60 degree apart. So comparatively to the previous case, here the 60-degree angle as compared to 180-degree angle offers more hindrance and more repulsion. So the CH3 molecule one will repel the another one. That's why the molecule will be high in energy, and that's why it will be less stable compared to the previous one. Next one being eclipsed conformation. Here what happens is that one CH3 molecule is covering, sorry, one H molecule, one H atom is covering the CH3 molecule, and the same with the case with the front carbon. So we can here clearly see that the energy barrier between CH3 and H with the back carbon is 6 kilojoule per mole, while the case is different when it comes to two H atoms. It is 4 kilojoule per mole. And the difference with the front carbon and the H molecule, H atom of the backside is 6 kilojoule per mole. That's why the total energy barrier being 16 kilojoule per mole, or we can say 3.8 kilocalorie per mole. So what this structure is trying to say is that in eclipsed conformation, one atom hides the another, or the front carbon and the back carbon are in total alignment with one another. That's why what happens is that it offers maximum repulsion, or maximum torsional repulsion. What this repulsion is known as is bond pair repulsions, which is greater in eclipsed conformation compared to staggered one. That's why eclipsed conformation, which we will study later on, is that is it is less stable. Okay, so yeah, basically eclipsed conformation can also be broadly classified into two different types, one being fully eclipsed and another one being partially eclipsed. So what we are witnessing in front of us is fully eclipsed conformation, and the total energy barrier being 19 kilojoule per mole, which can be summed up as 11 kilojoule per mole between CH3 and CH3, and 4 kilojoule per mole each between two pairs of hydrogen atom. Okay, yeah. So here it is brief description of what the Gauge conformation actually means. So a gauge conformation is unstable due to steric strain between two methyl groups. So the two factors come into play when it comes to stability of conformations. One being torsional repulsion and another one being steric repulsion. So steric repulsion is driven by size of the molecules. For example, let's say the steric repulsion between CH3 and CH3 is more because the size of the molecule being bulky, whereas the steric repulsion between H and H molecule is less because the size H atom is comparatively smaller than the CH3 one. That's why the repulsion between CH3 and CH3 will be more, which will result in less stability of the molecule, and that's why the molecule will be high in energy. So the gauge conformation is unstable due to steric strain between two methyl groups. Okay, next next present here is the wholehearted curve between potential energy and torsional the bond rotation. So what happens is that the first one being anti-conformation, in which the alignment of molecule is 180-degree apart, and the 180-degree being the angle of between CH3 of front carbon, CH3 the front carbon, and CH3 the back carbon. So the molecules are highest apart from each other. That's why the energy will be less, and which will result in more and more stability of the configuration. So we can relate these with our daily life as well, that when we are for example, the COVID situation here in place. So when we are locked in one room, so our we will crave for randomness, we will crave to move out. That's why we will be less stable in the room as compared to when we are outside. We are happily suited in the environment. That's why we will be more stable there, and we are craving to go outside will be less, which will result in more stability. Same the case here, that anti-conformation being 180-degree apart, the angle between the two methyl groups, that's why it will be less in energy, so it will be most stable. The next structure is partially eclipsed structure of the butane molecule. The angle being 120-degree, and so we can clearly see the spike in the graph here, that suddenly the graph raises from x axis to higher towards the y axis, and the energy barrier being 16 kilojoule per mole. So what happens is that these partially eclipsed structure is high in energy. That's why it is comparatively less stable. The next one being gauge conformation, in which the angle angle between the two CH3 molecule is 60-degree, energy barrier being 3.8 kilojoule per mole, and that's why it is somewhere in between the two previous structures. Sorry. Yeah, so these were the three scenarios. Next one is fully eclipsed conformation of butane, and this one is least stable of them all. The energy barrier being 19 kilojoule per mole, which is highest, and that's why this structure is less stable. So what happens is that after the 180-degree, 120 degrees and 60-degree cycle, the structures begin to repeat themselves. That's why the gauge, when we will rotate the CH3 bond, picking the one CH3 bond and rotating it by 60-degree, so it will again uh, set in motion the same structures again. So what will again come is gauge structure followed by partially eclipsed, when we will again rotate the gauge structure by 60-degree, so partially eclipsed structure appears, and next follows is that anti-conformation again. So this is the sequence. So what the conclusion drawn here is that anti-conformation being most stable, the reason for the same being less least energy present. The next one is partially eclipsed followed by gauge conformation, and the least stable of them all is fully eclipsed butane conformation. Yeah, so these slide present the theoretical aspect of what we had studied in graph so far. So the stability of the conformations depend on various factors, but the biggest one of them all are torsional strain as well as steric hindrance. So what torsional strain is that strain caused by the close approach of atoms or groups separated by three covalent bonds. So this was what we had studied in the previous slide. The second factor being steric hindrance. So steric hindrance is nothing but the congestion caused by physical presence of the bulky molecules. So this is what steric hindrance is. Nextly, if we can see the fourth slide again. So there are various other conformations as well apart from staggered and eclipsed conformation, but they are of less significance here. So we will see what briefly they are called as. So all the other infinity of intermediate conformations are called as skew conformations. So apart from eclipsed and staggered, various other conformations of butane are eclipsed conformation. And one important thing to keep in mind is that these rotations happen up about sigma bond, because sigma bond's electron cloud is cylindrically symmetrical. That's why uniform overlapping takes place. But if we try to rotate the pi bond, then what happens is that pi bond break apart. That's why the rotation is not possible, and these variety of conformations do not come into the picture due to restricted rotation in pi bonds. So this was it. I guess you all understood the topic, and thank you very much.